This talk is called Steps Towards Optimizing Scheduling for Linux Gaming, and I apologise for trying to mispronounce your name, by Changwoo Min.
Yeah, thank you for the nice introduction. I'm Changwoo Min from Igalia. Today, I'm going to talk about the steps towards the optimized scheduler for the Linux gaming. So in this talk, I'm trying to improve the gaming experience on the Linux platform by optimizing the processor scheduler. So this is the talk outline. At first, I'm going to try to convince you the gaming on Linux is something real. This is not a toy. This is a serious effort. And then I will actually show you, discuss about what metric that we need to optimize for. And then in order to design a good optimize the scheduling policy or optimize the scheduler, it is really critical to understand how the application behaves. So I actually share my analysis on game workload characterization. And then finally, I will introduce my own new algorithm for the scheduling algorithm named latency criticality aware virtual deadline, or LAV descheduling algorithm. And before explaining the LAV descheduling algorithm, I will explain the SCHED-EXT, which is the BPF-based extensible scheduler framework, which I used to implement LAV descheduler. So Linux gaming is here to stay, and this is something real. And one example is the Steam Deck. Steam Deck is the handheld mobile gaming device, as you can see on the screen. And Steam Deck actually can run x86 Windows games on Linux. So if you take a look at what's inside the Steam Deck, it actually has the AMD APU, AMD Van Gogh APU. AMD APU, of course, has the AMD GPU and x86 8 hyper-threaded CPU cores, right? And from the software side, it runs the SteamOS, which SteamOS is Arch Linux-based Linux distribution, and there's a lot of optimization for the Steam Deck hardware, especially for AMD GPU. And in order to run the Windows games on Linux, it actually has the Proton compatibility layer. And at the heart of the Proton, it actually runs the patched version of Wine for the performance improvement. And also it has a lot more, including the graphics related stuff, such as DX3K, VKD3D, and GStreamer, and FFmpeg. So when you actually think about the game, right, one of the most problem is that the stuttering problem. If you just search the stuttering and game on your favorite search engine, you're gonna see a lot of the questions and complaints about the stuttering problem. So stuttering problem also can happen that even after upgrading the PC, which basically means that some part of the stuttering problem is not actually related to the hardware, but also related to the software side. And by the way, the stuttering problem is nothing but the user experiencing some micro pauses while playing the game. And also the stuttering problem not only related to the Steam Deck, but also related to any gaming environment, including the PC and also the web games as well. So when you say that I'm trying to optimize the scheduler to improving the gaming experience, one of the first response that I got is that maybe scheduling might be not relevant in the gaming experience, because most games are GPU heavy. So if the game suffers from the stuttering problem, maybe GPU is the issue, right? But that's true. Most games are GPU heavy, but CPU is still the controller of the GPU, which actually initiating the GPU job. So if the CPU scheduling is suboptimal, GPU can be underutilized, and we can suffer from the stuttering problem. So in here, actually, I compare the two graph, which actually shows the frame per second over time, and the graph on the left-hand side actually run with the scheduler A, graph on the right-hand side run with the scheduler B. And as you can see in the graph, the left-hand side with the scheduler A actually shows a relatively stable frame per second over time. So in this case, that the user's gaming experience is okay. But in case of scheduler B, at some point that the frame per second soars over 120, and the very next moment it actually drops down to the 10 frame per second. So actually, in this case, that user can see a lot of micro pauses, and the gaming experience is really bad. So that's basically the stuttering problem. So overall goal is that somehow we wanted to improve the gaming performance to improve the the gaming experience. But when you say the game performance, what exactly does it mean? So performance means many different things. For example, when you say the throughput basically means that how much job can be done in a given time. And the another metric that we can improve is the latency, which basically represents the time to process the task. And if in most of the cases, latency is somehow very relevant to the throughput. But if the task is kind of parallelly executed, latency and throughput can be irrelevant. And these days, more important the metric in some domains like a game and the cloud services is the tail latency. Tail latency is the latency of the worst 1% or 0.1% worst case latency, which we call the 99 percentile or 99.9 percentile tail latency. So, and also the important thing is that the optimization strategy could vary depending on the optimization metric. For example, if we are optimized for the throughput or latency or the tail latency, optimization strategy could be different. So from this point, we can actually quantify the stuttering problem in this manner. So in the games, the frame per second or the frame time are the most widely used metric. And also the low 1 percentile, 1% frame per second is essentially the 99 percentile latency of the frame per second. And low 0.1% frame per second is the 99.9 latency of the frame per second. So not only average FPS, but also low 1% FPS are critical in the gaming experience, and especially a sudden FPS drop is also known as a stuttering problem. So when we actually optimizing the game scheduler for the gaming to improve the gaming experience is that my goal is that improve low 1% frame per second without hurting the average frame per second. So far I discussed about the Linux gaming in the Linux is something real. And then they discuss about we need to optimize low 1% frame per second, which is the 99 percentile tail latency for the frame per second, right? And then let's move on to the gaming workload characterization. So gaming workload characterization is understanding how gaming workload works is really important to optimize the scheduling policy, because that the optimized scheduling policy should reflect the actual behavior of the real tasks, which is the real task. So that's very important. So I actually end up spend a couple of months to analyze and understand the gaming workload behavior. So you don't need to spend time because I will going to provide a nice summary for that. So in some sense that if the games have some common characteristics which are different from the other general purpose programs, then we're going to have a chance to come up with game optimized scheduling policy. And that game optimized scheduling policy will reflect their gaming workload characteristics. Then that scheduler will work very well for the games and also the other workload which has a similar property with the games. So we analyze a lot of the data. So especially we actually collect all the scheduling traces and do a lot of the visualization and statistical analysis to understand it. And here is the summary. The first one is the task scheduling and about the task scheduling and the CPU utilization. So overall, around 300 tasks are scheduled while running a game, and around 9% task has long-lived task. which means that only 10% of the tasks are terminated. So, which means that fork bomb issue where the forking a lot of tasks is a kind of unusual case in gaming. And among 300, roughly the 10%, top 30 most frequently scheduled tasks takes 95% of the scheduling activity. And around half of them, around 50 most frequently scheduled tasks are a system task, which is especially the wine, graphics, and audio service layers, which takes 30 to 40% of the scheduling. And there are 50 to 20 game-specific tasks, which takes 60 to 70% of scheduling activity. So in some sense, the games mostly runs 30 to 40 tasks very frequently, and 60 to 70% of scheduling activities comes from 15 to 20 game-specific tasks. That's very understandable in some sense because that the many gaming engines creating their own thread pool, same as where the same number of threads are same as the number of CPU or 2x of the CPU. So that's very understandable. So another interesting thing is that CPU utilization is moderately high. So most of the game while playing the games is mostly about 65% to the 95%, but it never reached to the 100%. So that's understandable since the many commercial games are reasonably well optimized. So from the scheduler's point of view, many schedulers actually heavily optimize for the overloaded tasks, which means that the CPU utilization is 100, right? But that is a little bit uncommon case in case of the scheduling the gaming tasks. The next very super interesting thing is that the task execution time per schedule. So I actually measure the task execution time per schedule for while playing the games, and task runs for very, very, very short period of time. In most of the cases, it just runs a few hundred microseconds, less than a millisecond. And if on average and in maximum, it just runs a few milliseconds. And task execution time is very stable and predictable using its average, which basically means that the task execution time is the property of task itself. And especially some coordination tasks, such as the wine server, which is the server process in the wine Windows emulation layer. Its average execution time is about 260 microseconds. But some worker task, which is spawned by the game engine, runs more than 2 milliseconds. So this graph on the right-hand side actually shows the distribution of task runtime average per schedule in a game. And as you can see here, right, most of the tasks are run below 1 millisecond. So which is execution time is very short. That actually leads us to the question that what makes the scheduling happen? If task average execution time is such short, right? Then our analysis shows that the preemption caused by the exhaustion of the time slice takes only 25 to 30% of the scheduling activity, and majority of the scheduling activity, 70 to 75% of the scheduling activity, is initiated by the waiting system call, such as epoll, pipe read, domain socket read, and few tag wait. And in this case, task is first scheduled out, waiting for an event. Then it is scheduled in when the event is notified. And this pie chart shows that the call stacks which trigger the scheduling in a game. And as you can see here, right, scheduling preemption is just about 30%. And rest of them are epoll, field tag, and those kind of things. And another thing, so now we understood that the majority of the scheduling happens because of the waiting system call. Then now what I wanted to understand was that what was the waiting period right? That's the waiting time. And waiting time from one schedule to the another schedule is the task's behavior property. That's the waiting time that I define. And each task's waiting time is pretty constant, right? And this graph actually shows that the waiting time over time in a game. So in case of the wine server, most of the cases, it just waiting time is the 4 milliseconds. So in other words, wine server is nothing but waiting for 4 milliseconds and executing for 260 microseconds and keep repeating this process, right? And the right bottom hand side, the Chrome browser main process actually waiting for every 15 milliseconds, right? So other processors has some fluctuations and spikes here and there, but overall, the waiting time is pretty constant. And which basically means that there are very strong relationships between the waiters and wakers, and they are the main source of the scheduling activity. So we can actually create link the waiters and wakers through the edges and form a graph. And this graph shows that the top 50% of the waiters and wakers in two different games. And as you can see in the upper part of the graph, right? So these are all graphics related tests. So graphics related tasks spawned by the game engines do some job and then notify the signal to the DXVK CS task, and that actually let the DXVK submit task to draw the screen, right? So in order to draw the one screen, all these tasks are properly scheduled, right, and executed. And bottom side graphic, the bottom side actually shows that the audio related one. So the game actually do some audio related job that actually go through the timer related one, and it go through the Linux, the pipe wire thing, and then that actually generate the audio, right? So those are major observation, and here is the summary. So given the fact that a task has a stable execution time per schedule and the stable waiting time, we can actually say that the majority of game task shows a kind of semi or quasi periodic behavior. And another one is that in order to finish the one single job from the user's point of view, such as from a user input to display update or generating the audio, not only one tasks are involved to finish the one single job. A sequence of tasks are involved to finish the single job. And therefore, an accumulated scheduling delay in a task chain happens that will affect end user's experience, right? And that will eventually result in the sudden spike of the frame time or the breakage in the audio quality. So now we actually share the understand the game workload characteristics. Now switch the gears and let me explain my LAVD, latency critically aware virtual deadline scheduling algorithm. And then before explaining, then let me explain SCADEXT first. SCADEXT is the BPF-based extensible scheduler framework algorithm, which actually enables the scheduling policy to be implemented in a BPF program. And so the development procedure is somehow similar to the kernel module programming, but it actually inherits all the benefit of the BPF programming, so including the safety guarantee. So the procedure is writing the scheduler policy as a BPF program and compile it and loading into the system, and letting the BPF and SCADEXT infrastructure do all the heavy lifting to enable it. And the very nice thing of the SCADEXT framework is that the rapid experiment is possible. Since the BPF framework actually allow you to loading and unloading your BPF program, and also the BPF verifier infrastructure ensures that there is no infinite loop, and though there is no memory bug, it is impossible to crash the host or hang the course by using the scheduling your BPF-based scheduler. So no rebooting is required, which is good. And also BPF cannot crash your host machine. So the productivity is super good. And also SCAD-EXT, in order to use the SCAD-EXT, your BPF program should follow the GPL version 2, so it does not harm the ecosystem, Linux ecosystem. Actually implementing the scheduling policy with SCAD-EXT is pretty straightforward. So the underlying BPF framework provide the structure of operations, which is nothing but the collection of the function pointers. Actually, BPF program must implement a set of the callbacks. For example, as you can see here, set CPU, enqueue, dequeue, dispatch, runnable, running, stopping, quiescent, and yield, and there are so many other callback functions are defined. So essentially, when a task becomes the runnable callback will become run, will be called, right? And you can actually define the behavior when a task becomes the runnable by implementing and providing the runnable callback. And the task into the run queue or dequeue from the run queue, then these two callbacks are relevant. And task becomes running or the stopping. These callbacks are also relevant. So yeah, these callbacks will become relevant. So by providing the callbacks, you can actually implement the scheduler. So so having this in mind, so let's move on to the my LAVD or latency criticality aware virtual deadline scheduling algorithm. This is a new scheduling algorithm which I'm still developing and designing, which is basically motivated by the gaming workload. So, and actually implemented as a BPF scheduler on top of the SCAD-EXT framework. And theoretically speaking, LAVD is the proportional share scheduler. That basically means that the LAVD scheduler will respect the nice value to pursue the fair use of the CPU time. And also it is the virtual deadline-based scheduling algorithm. So not only pursuing the fair use of CPU time, it also has some notion of the urgency. So task deadline is used to represent the urgency of the task scheduling. But please do not confuse that this is not while this is a deadline-based scheduling algorithm, this is not a real-time scheduling algorithm. So even deadline here means that the relative execution, relative urgency among the task scheduling. So even though deadline is specified, there is no guarantee the task will be scheduled at that deadline. So please do not confuse that. The scheduler have to make many decisions. So, but in the LAVD, as name implies, the latency criticality is the first class factor in making the scheduling decisions. And the latency criticality is not given, so it is going to be inferred by observing the task behavior in a task graph, as we discussed when actually explaining the game workload characterization. The overall procedure of the LAVD algorithm is somehow similar to the other deadline-based scheduling algorithms. So under the LAVD, a learnable task has its time slice and virtual deadline. So which are decided by the scheduler. And LAVD picks a task with the earliest virtual deadline and allow it to execute for the given time slice. So this is nothing different here comparing to the other deadline-based scheduling algorithm. And the core of the algorithm is defining the latency criticality of the task. So as we discussed in the games that the many tasks are very tightly related through the weighting system calls such as EPOL and FUTEC, we actually leverage that property. So to simplify the explanation, suppose that there are three tasks, task A, B, and C, coordinated by the weighting system calls such as EPOL, FUTEC, or the domain system call or the I octal. And let me intuitively think about this, right? So let's think about how can we define the latency criticality of the task B. So we define task B is more latency critical in the following three cases. The first one is that task B's runtime per schedule is shorter. Then we can say that task B is more latency critical. That's because that if, in other words, that if task B's runtime per schedule is long, even though scheduling delay happens, that's relative impact will become relatively low. So that won't be the problem. So we can actually say that the task B's runtime per schedule is shorter, then task B should be is more latency critical. The second condition is that as task B wakes task C more frequently, that basically means that task B is the producer of the data for the task C. So if that's the case, then scheduling delay of the task B also delays the execution of task C, right? So that's very likely. So task B is frequently become the waker of the other process. That should be more latency critical. And the last condition is that task B wait for the task A more frequently, then task B should be more latency critical. That basically means that if task B becomes the consumer of the task A is a scheduling result, then if the scheduling task B is scheduling is delayed, then task C's scheduling is also delayed. So it is going to have that cascading effect. So these three factors, we scheduler continuously observe these three factors and decide the latency criticality value per each task, and using that latency criticality value to make a scheduling decision. So let's discuss about how those latency critical value are used in making determining the task's virtual deadline. So more latency critical task will have a tighter and shorter deadline. So the scheduler picks such a task more urgently or more other runnable task. I won't cover the specific very detailed algorithm, but this is the high-level philosophy of the algorithm design. And also, every this scheduling algorithm try to schedule all the in terms of the design, determining the time slice. So we actually, in determining the time slice, we try to enforce the fair use of the CPU time. So LAVD scheduler try to schedule all runnable tasks at least once within a predefined time window, which we call a targeted latency. For example, let's say that if the targeted latency is 15 milliseconds and two runnable tasks exist, then we are trying to equally divide the 15 milliseconds into the two runnable tasks. Of course, the details are a little bit more difficult, more complicated, but that's a high-level philosophy. So the scheduler proportionally divides the targeted latency as per task's nice value, priority. So it actually helps to enforce the fair use of CPU time. But just assigning the time slice per each priority does not guarantee the fair use of CPU time. That's because a task can be more frequently executed than the other task, or yield CPU more frequently before completely consuming its assigned time slice. So in order to enforce the fair use of CPU time, another additional trick that we use is deferring the task execution. So LAVD algorithm keep tracking how much time is being scheduled for the specific task. And if a task is overscheduled, we actually try to reduce the frequency of the task execution by injecting, artificially injecting some delay. And that differing duration is proportional to tasks over scheduled time. So that's all about the end of the our scheduling algorithm. And we are still, algorithm itself is still evolving and implemented. It's under the heavy development phase, but we got the early result, which is very promising. So this graph shows the frame per second result in one of the game's in-game benchmark. Yeah, so be careful that here middle is the 42 frame per second, here the middle is the 36. So graph cannot be directly comparable, but you can see the trend, right? So the upper graph is the result from the LAVD, and the graph on the bottom side is the EVDF, which is the default Linux scheduler from 6.6 kernel. And as you can see here, right, LAVD relatively frame per second changes are relatively stable, but in case of EVDF, right, you see a lot of the fluctuations, which causes the micro pauses and incurs the stuttering problem. So maybe I actually ran this game on the Steam Deck hardware with the 6.9 RC1 upstream kernel. So it is slightly early that the LAVD is better than the EVDF in the default Linux kernel scheduler, but result is pretty promising. And in many cases, LAVD provides better or similar performance than EVDF in terms of average frame per second and low 1% frame per second. That's all I have, and I'm happy to take questions.
Anybody have any questions? Yeah, sorry.
Could you talk a little bit about how you profiled each of the game processes to understand sort of critical path to reduce that latency, just so that I can understand how potentially we could apply this to other programs in our environments?
Are you okay to be muted?
Oh, so your question is about how to collect all this data and perform the profiling. So we actually use the PUF recording tool. So one of the PUF provide a lot of the options, and one of the option is that the recording all the scheduling activities. So we actually run the PUF record scheduling activities while running the game, and after the game actually playing ends, that we actually parse the PUF result data and calculate the execution time, runtime per schedule, and the dependencies between the callers and callers by parsing the result. So we will plan to open source the analysis tool in the future, yeah, when it is ready. Yeah. Any other question? Does it answer your question?
Yep.
Any other questions?
Thank you.
I couldn't quite see the graph showing EVDF versus LVD, the average performance. Could you read off what the increase was, please?
Excuse me?
Yeah,
Could you repeat the last part?
that slide. I see a horizontal line for average, but I'm having a hard time reading the numbers when I get close. What's the difference in average frame rate and P99 framework for the LAVD and EEDF benefit assessed?
I believe that I do not have the complete answer for your question, but what I'm expecting is that the LAVD essentially keep trying to find out latency critical task. and try to latency critical task more urgently. For example, while running a game, for example, wine server is going to always be detected as a latency critical task. And if you think about how the wine works, that every single Windows message have to go through the wine server, right? That's a kind of one of the current design of the wine architecture. And if the scheduling of the wine server is delayed, then every single operation of the Windows games running on the wine and Proton layer will become delayed. So since the LAVD efficiently and easily detect the wine server and promote and boosting the priority and by urgently scheduling it, so I think that's the reason that we can achieve the better average frame per second and the higher minimum FPS value.
Hey, thanks for the talk. I was just wondering if this is all publicly available and if I could like get to work on it and test it with other games. And
Oh, so the LAVD scheduling algorithm is publicly available. If you go to the SCAD-EXD GitHub repo, it has the couple of SCAD-EXD project repo in the GitHub. Then there are a couple of repositories. One is the SCAD-EXD kernel itself, and another one is the SCX folder, SCX repo. SCX repo has all the scheduler developed on top of the SCAD-EXD framework, and you will be able to find out LAVD scheduler under the SCX repo. You can try it, and also it is in all the many distributions, including the Arch Linux and the Debian, Fedora, and the Ubuntu provide the SCAD-EXD kernel, so you can actually change your kernel, which support the version to support the SCAD-EXD feature, and compile the LAVD. Then you can actually try LAVD scheduler on your desktop and laptop.
Got time for one more question.
Oh no, I was just saying thanks.
Okay. Any further questions? Well, thank you very much for your talk.
Thank you.